Thank you for the introduction. So we are going to consider the problem of outsourcing storage to third-party clouds. And it's actually now very common in a lot of enterprises. So it's shown that 60% of business data is now stored in the cloud. Now, there are two primary goals for data outsourcing. One is storage efficiency. We want to reduce the storage space in the cloud as much as possible so that we can save the cost. Another one is security. We want to protect our outsourced data from malicious attacks and even the cloud operators. So to reduce the storage overhead, one common technique that we use is deduplication. It's a kind of coarse-grained compression technique that if you have multiple copies of chunks with the same content, you only need to store one physical copy. And this is particularly attractive for backup workloads. And it's shown that it can reduce 10 times storage in backup workloads. So in this work, we also focus on backup workloads. To further improve security, we can combine encryption and deduplication. So we call this technique encrypted deduplication. So the idea is you encrypt the data, but you make sure that the key is derived from the content, so that after encryption, the encrypted chunks derived from the identical content will still remain the same, so that you can apply the deduplication in the cloud. And the cloud does not see your original data because it only receives the encrypted data. However, there are limitations for the encrypted deduplication. First of all, because it ensures that the same content will be encrypted into the same encrypted content. So it's deterministic. It will leak the frequency distribution of the original chunks. So it's subject to this frequency analysis attack. Another thing is the encrypted chunks cannot be further compressed. So because it's based on the deduplication, you can only remove the identical copies. But if they're not identical, but just with small differences, you cannot further compress them. So here we want to see if we can provide secure guarantee, we can achieve fine-grained data reduction, but at the same time provide security guarantees. And here we exploit trusted execution environments, TEE, to help us achieve this goal. And we use SGX as the motivating example. So the idea is we apply deduplication, delta compression, and local compression, do all things inside the SGX enclave. And the key technique for achieving further storage savings is by delta compression. So the idea is you have some base chunk M, and when you want to store a new chunk M prime, you can compute the content difference. So usually this difference is very small if they are very similar. So we only need to store the content difference, so you can still achieve further saving, even though they are not completely identical. And we protect the whole data reduction flow in SGX enclave. So the idea is the clients will encrypt the data. Right now, you don't have to apply the deterministic encryption. So you can build on existing symmetric key encryption. And then later on, the enclave will decrypt the data and do all these data reduction operations. And because it's inside the enclave, we assume that is protected from outside, even for the even for the cloud operators, they cannot see the operations and data inside the enclave. So this enclave will be provided by the organizations, and they will put the logic on the cloud. However, using SGX is still challenging, and the major overhead here is there will be high context switching overhead when you move the data across the enclave boundaries. And because for this delta compression here, we need to load the data from disk, and in order to compute the content difference. So you need to frequently load the data from the disk into the enclave, and then you store the delta difference back to the disk. So there will be a lot of context switching, and that will introduce high I/O overhead. So here comes our contributions. We call this ShieldReduce. It's a system that is supporting outsourced backup storage based on fine-grained shielded data reduction. And it's built on two techniques here. One is called the bi-directional delta compression that mitigates the I/O overhead. And also, it uses hybrid inline and offline compression to limit the I/O interference with the normal operations. And we conduct a lot of experiments based on real traces, and we show that it can achieve up to 3.5 times upload speed up, and also up to 3.6 times storage savings, and we also open source our prototypes. So the main idea here is that when you modify the chunk M into M prime, so we use M as the base chunk, and we delta compress M prime with respect to the base chunk M. Then we find that the neighbors of M are also likely the base chunks of the neighbors of M prime. So the idea is when you update the chunk, usually you will update multiple chunks within the same region. So in this case, the base chunks will also be clustered together, and this idea is something what we call the locality. Now, locality is a concept that is well defined, well explored in deduplication, and we extend this idea into chunk similarity. So the main difference is in deduplication, we focus on logical locality, while in our case, in this case here, we focus on physical locality. And because of this locality, because the base chunks are grouped together, so when we load the chunks, we don't need to load the base chunks one by one, but we can load the base chunks in a batch manner so that we can mitigate the I/O overhead. However, when you just load the chunks is not enough because the locality can degrade after you store a lot of backups. The reason is you choose one base chunk and you delta compress with respect to that, but after you store a lot of backups, you still refer to the very old base chunk and you apply delta compression with respect of that. So in this case, the locality will degrade and the base chunks will be scattered around. So what we want to do is to reconstruct the locality based on backward delta compression. So originally, we delta compress a new chunk with respect to the old chunk. We call this forward delta compression. Now, we do the other way around. We delta compress the old chunk with respect to the new chunk. And that's what we call the backward delta compression. So now we use the new chunk as the base chunk. So later on, when you store more backups again, you use this new base chunk, then you don't need to refer to very old base chunk. So because new chunk, old chunk, they are still similar, so it doesn't matter which one will be the base chunk. So in this case, if we use the new chunk as the base chunk, then we can reconstruct the locality. So that's the main idea. So let me give you an example here. Suppose that backup version v0 is stored, and when you store the new version v1 and you apply delta compression, so each new chunk will use the old chunk as the base chunk, and you delta compress the new chunk with respect to the old chunk. Now, when you store a new backup again, v2, you can actually use the new chunks here as the base chunk and delta compress the old chunk with respect to the new chunks. So in this case, this is the backward. And you can do backward and forward in a hybrid manner. However, if you do this backward, you also need to fix the old chunk and delta compress with the new chunk. So originally, we use C0 as the base chunk. Now, if you choose C2 as the base chunk, you also need to delta compress this C0 with respect to C2. So this backward delta compression will generate some overhead, and that's also what we want to do and want to address in this work. So we built a system ShieldReduce, and it's based on our prior work DB, which support deduplication, and we extend this to support also delta compression in order to achieve fine-grained data reduction. And the idea is we perform forward delta compression to achieve high performance on the write path. And also, we offload backward delta compression off the write path for storage efficiency. And remember that this backward delta compression is to reconstruct locality. So first of all, how do we define locality here? And it's based on the distribution about the base chunk. So consider a batch of chunks. We see how many base chunks, how they are spread across the containers. So the idea is, given a batch of n chunks, and then we have the unique chunks after deduplication, and we look at how the base chunks are spread, and we count the number of containers, let's say Q. So in this case, locality will be calculated as Q over n. So in here, for example, let's say you have a batch of 5 chunks, and the corresponding base chunks are spread across 2 containers. So in this case, Q is equal to 2 and locality is equal to 0.4. Then we use a threshold and we compare whether this locality is greater than the threshold or less than the threshold. If it's greater than the threshold, that means that they are clustered together, so locality exists, then we can perform forward delta compression inline. So in this case, we'll maintain a data structure called a delta index to track all the delta compression relationships. The details are in the paper, but the idea is we just perform forward delta compression on the right path. And if locality doesn't exist, we will prepare for the offline compression. So we add the information to some data structure called the backward index in this case, so that later on in the offline, then we can apply this backward delta compression. So in the offline, remember that we will choose new chunks as the base chunks and delta compress the old chunks with respect to new chunks. However, there are different groups of chunks that we need to do the delta compression, including the old base chunks and some new chunks that are supposed to be delta compressed with the old chunks, but now we delta compress with the new chunks. And also some of the already delta compressed chunks, then we have to choose the new base chunks and redo the delta compression. So the point is there will be a lot of persistent copies that need to be replaced when we choose a new base chunk. So this is how we introduce a high overhead, and we want to use a tunable approach to reduce this overhead. So the idea of this tunable approach is you don't have to compress everything. Maybe it's okay to allow some storage overhead, then you can trade between performance and also storage. So we have a user-specified offline reduction target alpha, where alpha basically means the percentage of physical space after the delta compression. So smaller alpha means to reduce more data. So the idea is, given an alpha, first of all, we sort all base chunks by the number of associated data chunks, and then we start with the old base chunks with the fewest associated chunks and apply backward delta compression. So we try to mitigate the overhead at the beginning, and if it already meets the target, we can stop right there. So in this case, we don't have to do all the delta compression. And for the remaining base chunks, we just simply store them without doing any delta compression. So that's the trade-off we make in here. So we built a system and we run the experiments on Alibaba Cloud, and we try different real-world and synthetic data sets. So these data sets are from different sources of application. So we want to see when these backups are from different applications, can we still maintain the same performance gain or the expected performance gain? So here we compare with three approaches that are based on SGX. The first one is our prior work, DB, which only performs deduplication and local compression, but there's no delta compression. There's another approach called Mega, which is also proposed in ATC a few years ago. It focuses on improving the performance of deduplication, but it does not consider security protection. So here, we faithfully implement the approach in SGX to make sure that it can provide the security guarantees, but we still maintain the performance advantages originally proposed in the paper. And also we implement this forward delta approach, which performs purely forward delta compression without backward delta compression. First of all, we look at the overall data reduction. Remember that alpha is our target, so smaller means you can reduce more data. So if we look at the column for alpha equals to 0, we can see that we can achieve very high storage savings, and compare with the DB, which does not do any deduplication, or secure Mega, we can achieve improved storage savings up to 4.5 times and 3.6 times. And it's also comparable to forward delta, but later on we will see that forward delta has poor performance. So the next thing here is inline performance. We show that in different workloads, ShieldReduce can preserve high performance on the right path with up to 3.5 times throughput gains compared to forward delta. It's lower than DB, of course, because DB does not do delta compression. Okay, but if you also apply delta compression, we can outperform forward delta. And also we consider enclave overhead, like how much context switching, then you can reduce. So here we use the number of O cores, which is the cores from enclave to the external applications. And we see that ShieldReduce can reduce the number of O cores by up to 83.3%. And most importantly, if you look at how much space that we can reduce per O core, ShieldReduce can achieve up to 4.6 times data reduction per O core. You may be wondering, hey, if you do this inline and offline, why not you just push everything offline? Then of course your inline performance will be the best. However, what we argue here is we need to do this in a hybrid manner so that for each O core, then you can still achieve high data reduction. If you do everything offline, then you need to do a lot of reconstruction. Probably each O core can only achieve a small amount of data reduction. So the key result here is to show that for per O core, we can achieve high data reduction. So this is the conclusion. ShieldReduce is a secure outsourced backup storage system based on fine-grained shielded data reduction. It combines bi-directional data compression and also hybrid inline and offline compression. In the paper, we also have more experimental results, particularly on micro benchmarks, and to identify how each component will contribute to the performance gain and what is the overhead of different steps. So you can refer the details to the paper. The code is open source, and we also got all the badges. Okay, so thank you, and I appreciate your questions and comments.